Hopefully everyone can see that. Let me know if not. But yeah, I'm so excited to be here for part two. So if you missed part one, we went all into vector embeddings, sort of how they work, how to choose an embedding model, etc. So this time we're going to take it a step further and go into vector search. And I'm a machine learning engineer at Weaviate, and Weaviate is an AI native vector database. So we'll be talking about how vector search works from a concept perspective, but then also going a little bit deeper and talking about how it works in vector databases and why you actually need a vector database. Yeah, so without further ado, let's get into it. If you're looking for a sort of text version of a lot of the stuff that's covered in this webinar, I would definitely recommend checking out this blog post. I wrote it back in November of last year, but it'll go through a lot of the concepts we're going to cover today, along with it has the code example that we'll cover for the how to implement vector search from scratch in Python. Yeah. You can also find these slides on slides.victoriaslocum.com, as well as my other slides as well. So first thing I want to start with is search systems kind of run the world. The way we interact with almost anything on the internet is search. And as much as they've gotten more sophisticated in the last year, the one thing that still stands true is that a good search system is sort of just normal. A bad search system is really, really annoying, right? If you're searching something on Google and you're not finding the right results, if you're trying to debug something and you're still using Stack Overflow or Google to find results for your bug and you're not getting anything, it's really annoying. If you're searching for some sort of fashion item on an e-commerce site and you're just not getting the right results, really annoying. So good search systems are great. Bad search systems really, really suck. And everything we do on the internet sort of starts with a search, whether it's debugging code, shopping for things on Amazon or H&M, or even searching through our own internal documents in our company. So search systems are super important. And the way they've kind of been built in the past is with traditional search or keyword search. So what keyword search does is it matches the exact terms between a query, so whatever the user's inputting, the search term, whatever you're searching in Google or in Zara or e-commerce sites or your internal company search system, and it matches exact terms from that query to all the documents in the database. So in this example over here, I'll have two documents, and basically what happens behind the scenes in a lot of keyword search systems is that these documents are tokenized and assigned a document ID, organized, stuff like that. And then when a query comes in, it's going to look through all the tokens in this table, and it's going to match the exact tokens and return the related documents. So this is great. I mean, this is what has powered search for a really long time. But the main problem with this is that you're not capturing the meaning of whatever you're searching for, right? You're just doing exact matches. And so if I search for Alaskan fish, it may not return the right results. So this can really struggle with conversational language. You need to have the exact right terms in your query in order to turn the right results. This also can struggle with typos and synonyms. There have been workarounds on this, so a lot of traditional search systems will make like synonyms lists. So for a word, you have like a bunch of synonyms manually written up in a document that then you either do query modification or document modification with those. But still, any sort of typos and synonyms, this can really struggle. Sorry about that. So what's the solution here? Vector search. So the main algorithm I'll start with is KNN, or K nearest neighbors. And this is when you're calculating the distance between a query vector and a document vector for every query and document pair. So we covered this in the last webinar, but when you turn a query or a document or anything into a vector, you're basically encoding its meaning into this multi-dimensional space. From that sort of string of numbers that represents its meaning, you can do calculations, mathematical calculations, that can then represent how similar or not similar two vectors are. And so we can use this in vector search to basically find the most similar documents to a query. So what sort of happens behind the scenes in this is that you will store all your document embeddings. You'll embed them with an embedding model and store all of them in a database. And then you'll convert your query when you get it to a vector embedding. And then you can calculate a similarity score for all your documents to the query by measuring the distance between every document in the query. And then basically you'll just return the documents with the highest score. So we can represent vectors in sort of a three-dimensional space. They're many more dimensions than 3 dimensions usually. But you can see here, like if our query was kitten, the most similar vectors would be like cat and dog and wolf. The vectors that are closer in distance, more different vectors like fruits would be farther apart. So closer distance represents higher similarity, and in this way we can do vector search by measuring distance between vectors. There's several different distance metrics that you can use in vector search, and I'm not going to go into detail in a lot of them. We have a nice blog post on this if you're interested in details, but what I want to get from this is it's math, right? You're taking a vector and you're doing math things to it, and in this way you're representing similarity with a score, with a math score. And that's basically it. So keyword search is going to return results that have the exact keyword match, right? So if you're searching for cola, it's going to return all the Coca-Cola products. Vector search, on the other hand, is going to return results with related meaning. So if you search for cola, maybe it'll also return Pepsi or Fanta or things like this. Similarity through meaning, not from exact keywords. So one thing I wanted to go through is just implementing a basic vector search application in Python, just to show you it's not that scary, it's not that hard. So I will switch my tabs over here. And again, this is in the blog post here, but I just installed 2 different libraries. We're going to use OpenAI for the embeddings just because it's easier, but you could use any embedding model from anywhere. And then NumPy is going to be how we calculate our distance between the vectors. So it's not that much code. I'll go through it really quick. So here I'm just importing all of our stuff. I'm importing my user OpenAI API key to get our vector embeddings. I'm starting an OpenAI client, and then I just have a few sentences here that we're going to embed. So best pizza places nearby, popular breakfast spots, etc., etc. And then I've defined a function here that takes in text, and it's using the text embedding small model from OpenAI. And then based on that text, it just creates an embedding and returns the embedding. And then here, I'm going through all the sentences here and just embedding them. So now we have a bunch of vectors, right? So in this function, we're going to take one of the math concepts here, cosine distance, and this function is just basically applying this cosine distance function into code form. Not that one, this one. So we do a dot product between our query vector and our document vector and a bunch of other math stuff, but TLDR, that's going to return a score based on how similar the query vector is to our document vector. And to get the most similar documents to our query, basically what we're going to do is we're going to get an embedding for our query. We are going to calculate for every sentence in our document set, so all the sentences up here, how similar, based on this cosine similarity, the query is to that document. We're going to sort them in terms of order, so most similar to least similar, and return that list and print it out. So if our query sentence is find the best pizza restaurants as close to me, and we run this function, we get 2 results. The top score is best pizza places nearby with a 0.7, and the next one is 0.35 with top rated seafood restaurants in Miami. So you see this one is much more similar than the second one. And even though we're not getting the exact same words in our query as our document, all of the right words, it's still understanding that that's much more similar. And then this one, it's saying, oh, it's kind of similar. I mean, top rated, best, food, restaurants, close to me in Miami have similar meanings, but it's still much different than this first one. So this is sort of how a vector search works on a very simple level, which is pretty cool that we can just implement that in like, what, maybe 20, 30 lines of Python. Yeah, so it's really not that hard to implement vector search. It's just math. It's just vector math. The weird machine learning part is really all in the vector embeddings for this, which is pretty cool. So the question then always comes is like, okay, so why do you work at a vector database company if I can just implement vector search myself? Why in the world do I need a vector database? Especially now that vector databases and vector embeddings are getting so big and there's so many companies offering vector search solutions. And the answer comes in performance at scale-ish, and also database functionality and operations. So we'll start with the performance at scale. So this algorithm that I just showed you of calculating the similarity between a document and a query for every document, the KNN algorithm, scales linearly. So for every new document, you're going to have one new operation when you're searching for something. So the more documents you have, the longer it's going to take. What I'll introduce and what most vector databases and vector search solutions use is called an ANN algorithm. And these have different performance and different feature functionalities available. But the main thing here is that they scale logarithmically. So with the more documents you have, the search speed is not, or the speed of what your results are going to be returned and the number of operations you have to do does not scale linearly. It cuts off at a certain point. And the way these work, the approximate nearest neighbor algorithms, is they trade exact precision. So when you're searching through every document and getting a score for every document, you get exact precision because there's no way you're missing a document, you're scoring all the documents, and you can return all the documents. But ANN algorithms kind of trade that off. So they trade exact precision for huge, huge, huge speed improvements. This means you can search through billions of vectors in just a few milliseconds with ANN algorithms, some ANN algorithms. There's many different ANN algorithms. There's trees like Spotify's Annoy algorithm. There's proximity graphs like HNSW, which we'll go into the next slide. There's clustering and there's hashing, and they all work in slightly different ways and have slightly different use cases. We'll focus on proximity graphs. So this little animation I have over on the right here is an example of an NSW graph. So without the H, we'll go into why that is in a second. I'll wait for this to restart. Almost there. Okay, so when we get all of our vectors into the vector space, we kind of form this graph between them. And when a query comes in, we need to find the closest vector to that query. So we start an entry point, and we basically hop through vectors, recentering on the closest one with every hop. So it's kind of hopping over here, and eventually we'll get to the space where this query vector is, and we'll be able to return the top results. Notice here that all these vectors on the left were not even scored. So this allows us to hop through this sort of graph vector space without scoring every single document like KNN algorithms need to. So this is an example of a graph and an algorithm. So taking this one step further would be HNSW. And this is my least favorite thing to say. It's called hierarchical navigable small worlds. Worst words to put together ever. But basically what HNSW does is it organizes vectors into a hierarchical multi-layered graph structure, which basically allows for really fast navigation through the dataset during search operations. So before, in this graph, we had to go through all these points, and imagine this graph is really, really big. We'd have to travel through all these different points just to get into the right area where the query vector is. HNSW does things a little bit differently. So when you're constructing this index, this graph, all the vectors start at the bottom layer. And then you take maybe 1% of the vectors and you bring them up to another layer. And then you take 1% of those vectors and you bring them up to the top layer. And what this allows us to do is when we search for something, we can basically hop to the place in sort of this multi-dimensional world where the query vector is a lot more quickly than we can on a flat graph. So query vector here is it's hopping over here, and then it can bring us down to the bottom layer, traveling from the top layer down to the bottom. Bottom layer has all the vectors, and we can return the approximate nearest neighbors that we get from that. This is an ANN algorithm, so of course there's no guarantee that we're going to get the real nearest neighbors, the true nearest neighbors from this, but it is really, really good at it. It's very accurate. It's one of the reasons we use it in Weaviate. And another reason we use it is it's also really, really fast. It's scalable and it's really accurate. So I want to say something else about this. Okay, so more high level, you can think of this as like, let's say I have a multi-layered graph about every noun you could ever think of, and I'm trying to search for ducks. And so on my top layer, I have three different things. I have an Eiffel Tower, and I have a rabbit, and I have a book. So rabbit would be the most similar. So I'm going to take that point and I'm going to bring it down to the next layer, and I'm going to expand it. And on this layer, I have a guy in an Easter Bunny costume. I have a specific long-haired rabbit, and then I have another picture of a I don't know, a goose. Now goose is the most similar, so I'm going to take that and I'm going to bring it down to the next layer and keep doing that until I get into the right space where I'm supposed to be, returning the nearest neighbors in that way. So in Weaviate, we have a custom implementation of this HNSW, hierarchical navigable small worlds, and an algorithm and index. And what this custom implementation has allowed us to do is add these sort of database functionalities and operations that you are accustomed to using. So that's create, read, update, delete operations and like tunable settings. So the problem with a lot of ANN algorithms is they don't out of the box support a lot of the things we expect from a database. So maybe you can't insert objects while you're querying them. Or maybe once a graph is created, it's stuck. And in order to add new objects, you have to rebuild the entire index. Sorry, monitor's going to turn off. So that's sort of the problems we were seeing, or not me, but the creators of Weaviate, Etienne and Bob, when they were first building Weaviate. And so that's why they decided to go with the custom implementation of HNSW. There is an open source library of HNSW. It's called HNSW lib. You can see it here. Weaviate is also open source, but basically what makes this a library instead of a database is it's lacking full operations and functionality. For example, one of those things was our delete functionality. So HNSW lib doesn't support deletes out of the box. If you go deep into the comment section of issues in HNSW lib, you'll find this from the co-founder of Weaviate, Etienne, where he's basically talking about how we implemented a delete feature in our HNSW implementation of Weaviate. It's very fascinating. If you're a nerd like me, I would definitely recommend checking it out. But yeah, that's sort of the difference between a library and a database, is supporting full create, read, update, delete operations, and also all the modularity functions that you would expect to have in a database. Okay. Vector search is not just limited to text. So if you were around for the last webinar, you remember that we went sort of into different embedding models that can handle different modalities. So for example, some embedding models can allow you to embed images or audio, or all of the above. And basically what these embedding models can allow us to do is multimodal vector search and other multimodal operations like RAG. So for example, we can do any-to-any search. So if you search text, it might return, if you search text like lions roam in the savannas, it might return an audio clip of a lion roaring, or an image clip or an image of a lion, or a video of a lion. And how this works is all these things are embedded via a very specific embedding model into the same vector space. And that allows just any out-of-the-box, like Weaviate function to search through the same embedding space with the vector. And then you kind of get multimodal search out of the box. We have a great Academy course on this. Weaviate.developers slash Academy, where you can work with multimodal data, and this uses a clip module, but we also support different multimodal embedding models. And then you could do multimodal RAG, for example. So we also have a multimodal RAG blog post that would be super great to check out. So all these different things allow you to do multimodal vector search, multimodal embeddings, stuff like that, and build multimodal applications. Second thing here is multilingual vector search. So another nice thing about vector embeddings is you can get sorry, my window's freaked out. Okay, you can get multilingual vector search sort of almost out of the box. So again, there are specific embedding models that can handle multilingual or specific languages in vector embeddings. And then when you ingest those vector embeddings into a vector database, you get multilingual search out of the box. So really all of this functionality is within your vector embedding model, not necessarily within the vector database. So a lot of this stuff you can kind of get for free as long as you choose the right embedding model, which check out the last webinar if you're interested in learning how to do that. And Leonie has a great blog post on using Weaviate with non-English languages if you want to learn more about that. Another fancy thing is called hybrid search. Hybrid search is really, really cool. So in the beginning, I talked a bit about keyword search and kind of that it's not great in a lot of use cases because it can't understand the meaning of things. And you need the exact right words in your query in order to return the right documents. However, there are still some use cases where you kind of want keyword search in your results. For example, if you're searching for a coding question on Google or Stack Overflow, and you're searching for a specific Python version, vector search is not going to be able to correlate that specifically necessarily, or not. Maybe you need to fine-tune an embedding model. But with hybrid search, basically you can add on keyword search to vector search and then sort of get the best of both worlds. So you can understand the meaning of your query with vector search, and then you can get specific term matches with vectors or with keyword search. So the specific Python version matching. And then you can return a combined result using a fusion algorithm. And you can get all the right context, including specific keywords, but also including the meaning that you get from vector search. And this is also offered in Weaviate as well. I'll go through that in a bit in the demo, but yeah, complicated concept, not necessarily complicated to implement. We'll see that in a second. Okay, the last thing I wanted to cover in the part where I speak a bunch is what does at scale really, really mean? So I talked about KNN algorithms, which scale linearly, and then ANN algorithms like HNSW and Weaviate, what Weaviate uses, that scale logarithmically. So with stuff that scales linearly, when do you kind of hit that cutoff point? Like when does it really become hard to exist with a vector search and you start to notice performance improvements without a really good algorithm behind it? Before we go into that, I think we sometimes forget the difference between numbers. So in this little graphic I found on the internet, you can see this little dot up here is 50K vectors, let's say. That's pretty tiny. then we can maybe go to 1 million, and it's still not breaking the bank. Like, we can do 1 million vectors easy in Weaviate. Like, this is not even breaking a sweat. Um, Around 50K, you might start to notice some performance improvements or performance degradations with like implementing your own vector search using the sort of canon algorithms I explained, maybe a little before that. But definitely when we get to that billion scale down below, that's an insane difference. I mean, this sort of blew my mind looking at this because I knew it was a lot, but like how much different 1 million vector is versus 1 billion vectors, or even 1 million versus 500 million. You can kind of visualize that. Um, Insane. Like thinking about doing that scale of search is insane. And another one here, just to kind of drive this point in, 1 million seconds is about 11 days. 1 billion seconds is about 31.5 years, right? So billion scale vector search, large scale vector search is no small feat. So when we say we do billion scale vector search at Weaviate, it's kind of a big deal. And we've been doing this for a while. So our first billion scale experiment was in 2022. We wrote a blog post on it using the Sphere demo dataset. And since then, we've now have customers running billion scale plus in production, which is really, really cool to see. And it's only going to grow, right? Like nowadays, it's almost easier to vectorize your data, all your data, than not. And so this is super exciting to see that this is the direction that we're going, and also that our algorithms and our constant improvements can keep up with this. Weaviate is built for scale, so besides our ANN algorithm, besides HNSW, and all the improvements we've done around that, we also have tons of different features that are basically meant for Weaviate to run fast at a large scale. That's not to say it's not easy to get set up. We'll see that in a second. I think Weaviate does a really good balance between having having things that you can tune and customize to your own use case, but then out of the box, you can kind of just use it right away too. So you can start off with a very simple prototype and then dive deeper and deeper as you need more specific things for your use case, because not every use case is the same, which we'll talk about more in the next webinar. Right, so we have features like quantization techniques to lower costs for storing your vectors and make searches faster as well. We have tunable settings to either tune more towards like accuracy or speed, because everything in machine learning is a trade-off. We have settings where you can change the different algorithms you use to do distance metrics, or change where your data is actually stored, break it up into smaller pieces, put some of it in cloud storage if it's not being used, some of it in memory so it's always available and super speedy, or some of it sort of in the middle in disk storage. So we have lots of different ways in which you can customize it. But the next part I want to go into is how you can actually use vector search in 20 minutes, 15 minutes. Okay, so I did this little notebook. And yeah, all these resources will definitely be sent out after. So I've already run all this, but I'll go through sort of how I wrote the code, why I wrote the code, and talk about why I ran it beforehand too. So here at the top, I'm just installing actually don't need that for this notebook, with the .env library. If I was running this in Python, the Weaviate client, which is their Python client. We have also other languages supported. JavaScript, TypeScript, Java, something else. I can look at that in a second. Something to measure how fast things are going, and the datasets library. So the dataset we're going to use today is this Wikipedia sample dataset, which has 10,000, which we're using 10,000 items out of. Yeah, so 10,000 is not a small number, but we're going to import them into Weaviate and do some super speedy searches. Okay, so first thing I'm doing is importing all my environment variable keys from Colab. And earlier today, I'm just gonna move that there. I need to move that again. I went into the cloud console at Weaviate and I started a little sandbox. So let's go over there and check out my sandbox. Okay, so this is my little sandbox here. If you missed the last webinar, the way you create that is you go up here, you click the plus, create cluster. You can do a sandbox free for 14 days. Gave it a name, I selected a cloud region, and I clicked create, and then you can see it over here in clusters. And then if you go to the connect button up here, you're going to see your URL and your API keys and a little code to get started. So that little code is basically what is here. So importing Weaviate and then connecting to the cloud, getting our URL, getting our key, and then also adding an OpenAI API key so we can vectorize our data. And client was ready. Next up, we're going to create our collection within Weaviate. So just deleting the collection if it already exists. And then we're going to use client.collections.create. The name is going to be wiki. So we can actually see that here. If we go to Explorer, and then we go to our sandbox that we just created, we have a wiki collection. I'll open that in a second. We're going to configure our vectorizer. So for this, we're going to use a name vector. You can actually upload multiple vectors per object in Weaviate. So we're going to call this one main vector. So for example, if I wanted to have a separate vector for the title versus the text, or group multiple properties in one vector, and then have a separate one for just the text, we can do that with name vectors. And then we're setting it to the text2vec underscore OpenAI module. The name is main vector, using that model, and these are the source properties. And then we're just creating our collection, and you can see that it already exists because I did it earlier. We're going to import the datasets Python library from Hugging Face, load dataset, and return just like the loaded dataset here. Next up, we're going to import all of our data into our Weaviate cluster. So getting our dataset, getting our collection that we created, and then inserting all of our data in our dataset, generating a UUID, and getting our vector, and then batch adding the objects. And you can see, can you see? Oh, you can't see. Okay, this took about 5 minutes when I did it. So actually not that bad, which would be cool, but time is money. And I want to spend all the time I have yapping at you instead of waiting for Wikipedia data to upload and Weaviate. Okay, so when we do all that, if we go into the Weaviate cloud and to our Explorer, into a collection, we can actually see our data here. So we have our UUID, we have our URL to our Wikipedia page, the Wikipedia ID, the title of the page, and then just a little text blurb of that, and then our vector, which is called the main vector, just like we set up. The dimension size is 1536, and you can even see the vector. And this is all of our data. So total object count down here, 10,000 entries. That's a lot. Let's go back to this. Okay, so now we can do some searches. So I'm going to get the Wikipedia collection, and I'm going to do the collection.query.near text. We can do near text because we specified a vector or a vectorizer in our collection. And do limit. So we specify our query then, so let's just change this to be fancy. I don't know, what do we want to search about? The history of the internet. Why not? Okay, so I'm going to search that. Oh no, I'm going to just make me run all this again, isn't it? Wait, let me see if I can just do this one. Nope. Okay. We're not going to do that then. Instead, I'm going to go over the little Streamlit app I made with all the same things. And I'll quickly show you the Streamlit code because I use the Streamlit Weaviate connection thing. I did this in VS Code. So again, I'm using the Streamlit Weaviate connection, which makes it super, super easy to build Weaviate stuff in Streamlit. I literally did this 3 hours ago, so I know. And then I am just getting our environment variables from my env folder. We're actually going to be able to search through 3 different modes. So we can do the keyword search offered out of the box in Weaviate, semantic search offered out of the box in Weaviate, and hybrid search offered out of the box in Weaviate. Get environment variables, clean the inputs, set up the sidebar, not that important. Here's the Streamlit part for connecting to Weaviate. So you can see we're doing st streamlit.connection, Weaviate connection, adding all of our stuff there. We can perform a search. So we are returning certain properties. We're putting in a query. This is a connection.query, doing different things. And then, yeah, just putting a query as a text input for Streamlit, giving us a search button, which then runs perform search, which will hopefully return cool stuff to us. Okay, let me go back over to the Streamlit app now and actually show you how this works. Make sure I'm sharing the right window. Okay, so this is my little Streamlit page, Streamlit thing that gets up when I run Streamlit run app.py. And let's just search here, history of internet. Please run. I hate doing live demos. Okay, yay! And now from our semantic search, we get different results. So we can go over to this Wikipedia page. It's about earliest internet stuff. Nice. Or this one, Firefox release. That sounds like a history of the internet. So you can see all these results are pretty relevant. Let's go over to hybrid search and see if we get different results. Okay, slightly different results here. You can see this one's a bit different. Maybe a bit worse, but I'm not sure. And if we go over to keyword search, way different. Okay, so now we're getting Norton security, internet slang, not super relevant. The internet page, yeah, maybe. But you can see these results definitely are not as good. So because it's not understanding the meaning and intent behind that word. Okay, let's do another query. Anyone have anything that they want? Let's do vector search. Asking vector search application about vector search. It's like Inception. Google search, depth first search, Viridian, keyword. Interesting results. Let's do hybrid. Interesting. Yeah, super fun. So anyways, this is one such demo just to show you that it's super easy to implement vector search. Again, this is the, no, that's not the query. This is the query. Nope, still not the query. This is the query that you can use to basically perform vector search. This is all the code you need to perform vector search, maybe even less if you do less data insert problems. You can see a lot of different examples of this in our recipes repository. Let's go on this link. So in our recipes repository, nope, not that one. We have Weaviate features, and you can go into bring your own vectors or hybrid search or named vectors and all that, and also see different examples in our docs, which are here. And how to search, you'll see image search, keyword search, hybrid search, multiple target vectors, re-ranking, etc., etc. So lots of fun stuff to discover. And you'll notice that our hybrid queries are looking very similar to our keyword queries, which are looking very similar to our vector queries, right? So this is just out of the box functionality that you can play around with and optimize for your specific use case. Okay, I think I'm done yapping for now. Oh, more advanced, fun Streamlit app is this one that my colleague JP made. Would definitely recommend checking this out and also checking out the blog post he made with Streamlit for this. But for example, where you could take this to the next level, which we'll talk about more next week, is adding search to sort of a chat system. So adding search and generation together. So if we search romantic comedy for a date night, it's filling in that there. So basically what this is doing in the background is it's searching through Weaviate using this query, and then it's getting all these results back. And in one query, we'll see this next week, you can even give it to a large language model to give you a text response back, a summary response back, or insight from the response back. So definitely stick around next week if you want to learn how to do this. I will start answering questions now. And I'll leave that up while I start reading all these questions. Okay. How is storage optimized for high-dimensional vectors and 1 billion embedding size dataset to balance cost versus performance apart from indexing? Great question. So again, lots of different options to do this. One of the main ones is vector compression. We also have a great Academy course on this, and we offer several different types of compression. So product quantization is a type of compression, binary quantization is a type of compression. And basically, what this allows is the vectors to be smaller, so they're more cost effective, and they also speed up the vector search process. Sorry, I lost your question. Go look at it again. Another thing Weaviate offers is called multi-tenancy. So this is great for use cases that are maybe like user-based. So you have like one collection per user, things like this. So basically what this does is Weaviate splits up the collection into multiple tenants that are actually completely isolated. So for example, if you have a user-based product, you don't want Adam's search to suddenly go into Daisy's results, right? You don't want Adam to be able to access Daisy's data. That would be really, really bad. And so our multi-tenant system completely isolates individual collections. But then this can also be used for really efficient, large-scale vector search, right? So you have smaller collections, that's nice, but then you can also do things like manage tenants in different storage tiers. So you have different costs associated with each of those, stuff like this. There was one more thing I wanted to say about working with vectors at scale. It's gone. But anyways, there's lots and lots and lots of different things that Weaviate does and allows you to sort of manage to optimize embedding like large size data sets to balance this cost versus performance. And as I mentioned, we have customers right now running billion plus scale vector search in production, which is really, really cool. It is possible. Also, for that little snippet, I just asked our Kappa AI widget, which if you don't know Kappa AI, it's a super cool docs question RAG product that uses Weaviate. So we're using Weaviate to use Kappa AI to then search Weaviate docs. But you can ask anything like, does Weaviate do billion scale vector search? And it gives you a really cool RAG response. Okay. Yeah, So the next question, how does Weaviate handle real-time updates or incremental indexing for dynamic data sets? Weaviate is super good at handling real-time updates, real-time deletes, also like querying while inserting, querying while deleting. We have a lot of customers also doing this in production at a very high level. So the way we do this is not necessarily the easiest to explain in the time I have left. If you have further questions about this, definitely reach out to me on LinkedIn, and I can answer further. The short answer is we do like background async cleanup processes within the graph to maintain sort of the right structure and all the querying processes. But yeah, a little more complicated than that. Okay. Is the range in Streamlit the embedding size? Here? No, this is the year range of the when the movies are released, which is a property within Weaviate that then we're using a filter. But there's a blog post that goes in more on that. I will definitely send all these resources out after. How does vector search deal with typos? Great question. Okay, so when a vector embedding model is learning all of its knowledge on how to turn text into embeddings, it's also going to come across some typos in this really, really large amount of training data it's ingesting, right? So when it's looking through all of the internet, it's probably going to come across recommendation spelled with one M instead of two, which I do all the time. So basically, from those small occurrences, it's going to be able to learn that, okay, these mean the same thing. Um, Again, it's probably not going to be as good as using the exact right words with no typos, but it's still going to work. For example, how can I spell a word wrong here? History of the internet. I really hope this works because otherwise I'm going to be really embarrassed. But I think this, yeah, it should pull up the same results, basically. Um, so basically, it's all in the embedding model. When it's learning from millions and millions and millions of words, it's going to pick this up. How does AI agents work with RAG and Weaviate multi-agent workflows? Fantastic question. We will talk about this in detail next week. We also have a really great blog post probably published tomorrow, which we'll talk about it more too. But yeah, join next week. We'll talk a lot about that. And I think Data Science Dojo also has some great events coming up about AI agents. Oh, yes, I will get to your question. Okay, no dumb questions. Absolutely never. Okay. So if you encode the image of a tiger and also the word tiger, you would expect that the vector would have a similarity. Yes, absolutely. So you will get the original data back. For example, in Weaviate, you can store both the original object and also the vector in like one little object. So in our, you can see that here, like this is one object and the vector is stored with the original data. The same thing happens with multimodal data. So the image would be stored in here in probably a base 64 format or something like that. The model is basically learning again through tons and tons of data, the embedding model, that those two things are similar. And so it's all in the embedding model and what it was trained on to figure out that the text tiger and the image tiger are the same thing. So that's why like having embedding models trained specifically for multimodal data is really important, but also why they're not as good because finding those data sets is a little bit harder than just, ingesting all of the internet to get a text embedding model. I hope that answers your question. Let me know if it doesn't. Oh my gosh, so many questions. Okay. Um, okay, good questions. So the algorithm, the HNSW algorithm in Weaviate, the index is implemented in Golang. So Weaviate, the database, is implemented in Go. Um, for algorithm implementation, I would say that Python is never really used. But basically, to interact with the database, we offer several different clients. Um, Where's my developer docs? So we offer a Python client, a JavaScript client, a Go client, a Java client, and also a GraphQL client. And so the database is built in Go, but then these clients allow you to interact with the database, if that makes sense. Um, yeah. Yeah, so structured data, not exactly sure what you mean by that. The data we have here in our thing, I would actually call unstructured. So this is just sort of messy text, right? We're not extracting any sort of properties out of that. We're just getting the title, the text, but this could easily just be like a blob of text that has been chunked, stuff like that. As far as extracting features from unstructured data, we'll talk about that more next week when we talk about agents, for sure. Great question. Weaviate definitely supports BM25 search. It is our keyword offering for keyword search. Um, so for those of you who don't know, BM25 is a pretty popular keyword search algorithm. It's complicated. I'm not going to go into how it works right now, but I did do a webinar about a while ago going into hybrid search. I don't know where that webinar is, but I can send the link later. But basically there I talk about exactly how the BM25 algorithm works, how it works at Weaviate, why we use it, et cetera, et cetera. Okay, okay, okay. Why do we use Go for our algorithm implementation? Not really sure. I think HNSW lib was written in Go, and because we based our version of HNSW on that open source library, we decided to be in Go, but probably because it was like is a very like base functional programming language. And I don't know, message Etienne on LinkedIn. He'll tell you more, but for sure. All the notebook slides and resources will definitely be shared. If you haven't signed up someone with your email, definitely go sign up for the next webinar because I'll send out like long form resources that I might not get to um, later in further emails when the whole webinar series is done. And also follow me on LinkedIn because I can post more on there too. Go is awesome. Also, have you seen the gopher, the little mascot for Go? The best. Nothing better. Um, what other questions did I miss? How does hybrid search in case of search engine work? So it works mostly similarly. Again, I would definitely check out my hybrid search webinar for a deeper dive into that. But instead of just vector search or just keyword search, you're doing both at the same time behind the scenes. And then you can use different what are called fusion algorithms to basically take the results from both vector search and keyword search and smash them together doing more math stuff and then return the most related results from both. Okay, yeah. So how do different vector databases, what makes different vector databases different? Yeah, so you're right about the fact that a lot of indexing techniques would be almost similar. I think a lot of the other sort of AI native vector databases are using HNSW or something similar to it, but it's probably a lot in how they optimize their search, but I would say more so in sort of the offerings around the database. So, for example, hybrid search is not something a lot of other vector database companies have. It's something we've built into the sort of core functionalities as Weaviate, that we thought it was really important to have a keyword search offering that's able to scale well on top of vector search to be able to handle these sort of multifunctional use cases. Um, Other things like we have a module system that allows us to kind of pull out and plug in any different models, both for embeddings and for generation. So for example, for Cohere, you can have text embeddings or multimodal embeddings or generative models or re-ranker models. And it's super easy to interchange these different models, work with the provider that you need. Another differentiator is definitely like how you can deploy Weaviate. So where you can use Weaviate. Um, where is that? I don't know where that is anymore. They move stuff around occasionally on here and then I can never find it. Oh, here we go. Yes. So for example, we offer Weaviate Cloud, which is where we use the sandbox today. You can also deploy with Docker, you can deploy with Kubernetes, you can use our embedded version of the database. Um, so all these different options for that. Uh, hopefully that helps. So I guess it's more on the features as than the actual like indexing implementation, which I went into super deep dive today.